my talk will actually echo what Jeff Dean just covered, but what I also worry about is whether the IC design engineer will lose our job. Well, starting with this subject, I'd like to start with a general definition for AIoT. AIoT, as my definition, is the connected devices with intelligence. And that definition will be going throughout this talk. As Jeff just covered, for the past decade, the advancement of neural network, as well as the Moore's law, actually Moore's law is probably playing a very important role to enhance the computing power, the computing efficiency. All these factors add up to make AI machine learning using deep neural network possible. And artificial intelligence in the past decade start to revolutionize everything we have in almost every area we have, from finance, automotive, healthcare, education, and many, many more areas. The connected devices started with laptop, smartphones, and advanced to lots of Internet of Things. Today, we already see like tens of billions of connected devices in the world. Many of them are equipped with artificial intelligence. The improvement of the technology to collect data, to send data, to store data, further advanced artificial intelligence applications to even more devices. As a result, the resulting traffic on the internet also goes soar. It's estimated by the year of 2030, there will be greater than 350 billion AIoT devices available in the world. And by the same year, it's estimated that 1.4 zettabyte per month of internet traffic will be available. AI also has big impact to the global economy. By the year, again, in 2030, we estimated the impact of AI is roughly at 13.5%. This number may differ from region to region, but it will definitely affect many, many jobs like a circuit design. We estimate about more than 300 million jobs of skilled or unskilled workers will be affected. And for circuit designers, we are more concerned about semiconductor IC business. As we always know, semiconductor is the real push hand for the high tech, and high tech is the real push hand for the global economy as well. This number will again follow a healthy trend of growth. To 2030, we estimated the revenue will reach up to $780 billion. That's about 1.8x as of today. Now we're showing a minute of video.
On the go and at the office, enrich our daily life. From biometric sensors that track your sleep to voice assistants and smart devices around the house, Edge AI devices interact with the real world, tailored to personal preferences. These devices also interact with cloud services, using the latest communications standards. Intelligent automation and seamless communications will enable a cascade of machine-to-machine actions. In the car, Sensors and cameras benefit from Edge AI. Together, this will drive the future of autonomous vehicles, while 5G V2X will keep you and your car connected to the world around you. Over the next decade, it's expected up to 50% will work remotely. Therefore, low-latency 5G communications and Edge AI is essential to make the virtual office seamless and efficient. MediaTek's expertise in computation, multimedia, communications, and integration makes us perfectly suited to advance new platforms and applications for the AIoT era.
As you just see from the last part of this video, it mentions multimedia, computing, and communication. They're serving, like this figure shows, 3 big trees of technology. We also call it technology pillars, which will help to grow lots of leaves of AIoT applications. The application could range from personal voice assistants, robots, or automotive, and many, many more applications. As a career IC designer, I'm even more excited to say that we're also the water or fertilizer to help on the root side. We're contributing lots of technologies, and as this figure shows, we are contributing many papers to ISSCC in next 3 days. If you're interested, please feel free to join us. AIoT platform cannot work alone. It's formed by edge device, pipe, which has the communication technology in there, and the cloud, which is the main location for data center. With the technology pillars I just mentioned, I replaced them into their functional position. For computing, multimedia, communication, they are fairly distributed in these 3 different areas. In this presentation, we will explore into 3 areas which associated with each one of them. The first one is Edge AI SOC, which is the enabler for edge device. The second part is for wired and wireless connectivity, which is the enabler for the pipe. The third part, I am not going to cover too much on the difficulty of AI and computing at the cloud, but I would explore different kind of hardship with interconnect, process, and package issues. First part I'm covering is Edge AI SOC. Traditionally, or still nowadays, majority of AI operations has been done at the cloud. Cloud computing does offer quite a lot of advantages, especially computing resources. It has less stringent power limit or thermal budget. However, there are many use scenarios that would demand either a fast response time or always-on availability or high security privacy, or to be more energy efficient to work standalone. AI has moved to edge devices that put extra challenges for algorithm, system, and hardware developers to pursue. I'm taking an example for vision or visual perception or recognition. Just a few years ago, the computing requirement would only support like 0.1 teraops at about 1 TOPS per watt. Just last year, this number has been advanced to 1 TOPS at 3 TOPS per watt. And in the future, we believe on the edge devices, it will soon reach 100 TOPS at about 30 TOPS per watt. Of course, a lot of contribution are from Moore's law, but also this is really demanded with a diversified workload and increasing computing demand. This kind of computing power would enable multi-streaming on the multi-mode AI with the assistance of 5G service to support the state-of-the-art augmented reality, extended reality, etc. Here I'm showing an example which is another demand for edge AI. That's on the edge side of SOC, it requires concurrent multitasking. This example is a 3D human post-traction which drives robots in real time. This is under constraints of a limited thermal and memory budget, where the building blocks like image sensors, ISP, CPU, GPU, APU, these processes have to work concurrently to perform different functions. And for the connectivity, Bluetooth, Wi-Fi, they have to be on as well to transfer data or transfer controls to the robots. Therefore, we have seen certain demand and which have posed some challenges for edge AI SOC design. The workload has been advanced and diversified with the constraints on the computing power and memory and thermal budget, etc. So we have some directions to mitigate this issue by maximize the processing efficiency and to minimize the development effort. Here, we're providing 3 technology directions which are following these directions. One is the specialized hardware and system design. The second is design automation. The third one is an integrated and flexible SOC platform. This slide, I'm going to introduce on the necessity to develop artificial intelligence processors unit. We also call it APU. Deep neural network has been developed to compose of a lot of repetitive operations. CPU and GPU are more like either general purpose or parallel processing for some general purpose. With the development of APU, specialized for most frequently used operations, if we port the algorithm from CPU to APU, for example, we use a face detection case scenario here, we're finding it can achieve like 20 times faster or 55 times lower power reduction. In this conference, MediaTek is introducing a specialized hardware for edge AI SOC. This IP features 1 to 10 TOPS at merely less than 1 watt power budget and at less than 10 gigabytes per second DRAM bandwidth. This would make the edge SOC AI operation possible with many advanced features. There are multiple data precisions available. Also, it supports versatile network topology and diversified workload, as I just mentioned earlier. For the design automation, we're also applying AI-based deep neural network. In the past, deep neural network design usually started with network selection, with parameter training, network reduction, and a lot of optimization work with hardware has to be done manually. This work is very labor-intensive or brain-intensive, requires a group of engineers to work for more than 3 weeks to get the best result. However, when we apply AI to automate this process, after we set the right constraints, we let the AI or the machine to run by itself. It takes only 3 days to get us the best result. With this kind of capability, we're able to effectively improve our productivity quite a lot. I'm putting an example here which uses Inception v3 for image classification. This example shows that with manual migration, APU can comfortably reach 14 times faster than CPU. However, with AI optimization, we may go either for speed, about 2 times faster, or we may go for accuracy improvement for roughly like a 4% improvement in this case. Or we can actually balance our optimization to somewhere in the middle. This gives us more flexibility in our design for artificial intelligence. Also, it's required to have a flexible SLC platform for the developers for varieties of applications like face detection, interaction, or the voice recognition applications to run at different products or platforms like a smartphone, TV, and for vehicles, etc. To make this kind of platform, we are providing the framework API as well as the SDK toolkits to make the developers easier to optimize for heterogeneous computing among CPU, GPU, and APU, and will be able to utilize based on different operating systems like Android and Linux. That concludes our AI section for Edge SoC. We're advanced to the topic of connectivity, where we're gonna a bit focus on PhiG. I'll explain the reason a bit later. This slide simply explains how the data traffic affects the demand for the higher data rate. We can see for the 5 years period between 2017 and 2022, we're seeing about 3 times in 5 years time frame. where we're seeing majority of the growth actually comes from the mobile wireless. This slide actually shows wireline and two different wireless standards. For the wireline, of course, it runs a bit faster. Wi-Fi runs in the middle, and cellular runs in the bottom. We're showing that it almost starting around 1995, we're seeing about 10 times of the bandwidth within 5 years kind of growth rate. This has been very consistent until today. And this is also after the introduction to terabit Ethernet and tens of gigabit per second for Wi-Fi and multiple gigabit per second for cellular phone. However, 5G is not just about higher data rate. For the 5G service, there are 3 feature vertices. Of course, higher data rate, that's what we call enhanced mobile broadband. That's basically for smartphone, mobile phone. But there are other aspects of the features of a 5G service. One is called ultra-reliable, low-latency communication. This is extremely suitable and required for vehicle or for automotive applications. The other side, the other vertex, is machine-to-machine, massive machine type of communication. This is extremely suitable for IoTs. So we can comfortably say 5G actually enables AIoTs in various, in all kind of devices. You know, they need all 3 of these kind of features. We can see smart IoT devices can leverage 5G as a security camera, smart wearable, or voice assistant devices. On the other side, we have high-band real-time applications like augmented reality, virtual reality. And on the bottom side, we're seeing like a drone and truck trackers applications available for 5G. 5G does not come for free. 5G actually is very, very complicated, and it actually accumulated 4 previous generations of legacy. This figure actually, on the left-hand side, actually shows the number of pages of RF specifications. On the leftmost side is the first generation analog. It only takes like 136 pages. In the 5G new radio, accumulated with all the previous generation, we have found it's like 13,000 pages. That's about 1.3 meter thick. And this results in gate count increase as the right-hand side of the figure shows. This is a real example of MediaTek modems, starting from 2nd generation to 5G millimeter wave. And we can see that 240 times of gate count comparing of 2nd generation from the 5th generation. However, the area or the die size is not so bad. But I think this is really thanks to the process scaling. We want to thank Moore's Law to continue. The other part of 5G, in addition to modem, is the RF transceivers. Actually, for 5G, 4G, or even for Wi-Fi, the modem actually puts more limit, push more limits to Shannon's law. Therefore, people are using carrier aggregation, multi-input, multi-output, higher bandwidth, higher modulation scheme to achieve higher and higher data rate. But this does not come for free. Transceiver area is not so easy to scale, mainly because they're analog or RF intensive, and also the technology it adopts is usually 2 or 3 generations behind the digital. Here we show MediaTek's ISSCC publication in the past to show this area growth of the transceivers. But it has benefits a lot for the energy efficiency. Just for cell phone alone, the modem actually power or energy efficiency improves drastically over the past 10 or 15 years. However, we also observe it's converging with Wi-Fi since the standard of 11ax. I will use this slide and this chip to conclude the connectivity and edge SoC. This is the first 5G SoC implemented in 7 nanometer. It's a full SoC for smartphone. It's currently in production. It combines the technology pillars I just mentioned, computing, multimedia, and communication, inside this chip. On the processor side, CPU, GPU, and APU are integrated with multi-core generally applied to all the building blocks. On the multimedia side, ISP, or image signal processor, has adopted HDR image processing. On the connectivity side, with integration of 5G modem to achieve a 4.7 gigabit per second performance. Also with the connectivity block with Wi-Fi 6, GPS, and Bluetooth. This chip actually produces a few papers in this conference. If you're interested, please feel free to join. Next, we're advancing to the topic of interconnect process and package. As I just mentioned, these technologies are actually intertwined with each other, and they're very much correlated with data center technologies. And data center is basically what we call today as the cloud. This chart actually shows the increasing demands on the cloud and also show the growth and actually the ratio of hyperscale data center. The growth rate is okay, not very significant. However, what we want to watch on is this ratio actually started to take up as the majority computing force for the data center. Within these data centers, the traffic either to outside, between data centers, or within data centers. We also found that within data center, data traffic accounts for almost 70% of the total IP traffic. This makes a lot of traffic actually consumed inside, within data center. We want to address on the process limitation, then we advance to why we want to cover the package and the interconnect technologies. This curve on the left-hand side actually is the Moore's law. The Moore's law actually continue nicely with still with twice our gate densities every 18 months, thanks to TSMC. However, we're facing more and more challenges at the power density side. First, on the dynamic power, this number actually reaches 380 watt per centimeter square on 7 nanometer technology. Another headache has been the leakage power. Fortunately, with the introduction of FinFET technology, we are able to bring this number down by almost 2 orders of magnitude. Another limitation we have observed is the cost. Although we continue to increase the gate density following the Moore's law, but the cost per transistor cannot follow as well. Another even more risky factor is the design cost. This is really due to the complexity of the chip design when the gate count start to get more in the certain area. And also the process step getting more complicated. You can see this trend. The design cost becomes astronomically high, which prohibit many smaller companies to use the technology. The third limit we want to discuss is the yield due to the defect density. As we can see, the larger die would yield less, would yield lower. So it's desirable to separate the die, which we can make them still integrated on the same package as we call homogeneous integration. Therefore, the chiplet technology has gained more interest in recent years. We use this technology to achieve more than Moore's law. First is on the homogeneous integration, as I said, to overcome the defect density issue, and also provide better scalability of the die. The second would be heterogeneous integration, which we can use a different process. We have more flexibility on the IP. We have more flexibility on the process selection, and it may become more cost-effective. However, for these arrows I put there, we are seeing more and more challenges to interconnect these building blocks together into a chiplet. Our development of advanced package really starts from single chip, single die, SOC package. On the consumer side, we're advanced to several different kind of packages with multi-die. But it's more difficult actually to implement or to design high-performance computing packages, such as CoWoS or info technology. This photo actually shows MediaTek's data center switch. This one is running at 6.4 terabit per second, but just recently we announced the production of 12.8 as well. We featured this one as the world's first, the biggest dual die homogeneous integration info package applying MediaTek M-Link. That's the chip-to-chip interface technology. Interconnect has put a lot of challenges. In this figure, we're seeing the off-chip I/O bandwidth rise 10 times for every 5 years. But the pin count can only accommodate like 1.7. This put a huge gap for the off-chip bandwidth density. Therefore, interconnect technology needs to be developed in package, on board, and off board. Here we're presenting a technology, a SerDes block we use for either on-board or on-chip communication. This features first 7 nanometer DSP-based SerDes with the scalability, with the integration capability for SoCs. 112 gigabit per second, employing PAM4 modulation scheme. And we can also demonstrate that it actually scales well with the process from 16 nanometer to 7 nanometer to gain the area and power advantages. If you're interested, please feel free to join us for the presentation this afternoon. I'm coming back to this chart. As I just said, we as career IC designers, we're just like water, we're just like a fertilizer. We're helping fertilizing AIoT from roots to leaves. I'm using this figure of future to conclude my talk today. We believe AIoT applications will be blossom to flowers. The 3 technology pillars still remaining computing, communication, but more interaction should be there instead of just limited to multimedia. There are many, many technologies for us to pursue. Many of them are suitable for IC designers like us. In next 2 talks, actually, we also cover in the small block here, like quantum computing or advanced process technology. Our next 2 speakers will cover them well. I want to thank everyone for listening to this talk. My special thanks goes to Yunxiang Su, Conan Zhan, and many wonderful colleagues at MediaTek. Thank you very much.